Good morning, everybody. Welcome to our SAIMM webinar series. Today's topic is towards a sustainable supply of metals and minerals using life cycle analysis for mining project impact assessment. In today's global world, we all know how important life cycle assessment has become. So I'm personally looking forward to hearing our speaker today discuss this topic with us. Tijsseling is a sustainability manager at Minviro, a spin-out company from the University of Exeter. Minviro supports mining companies in adopting life cycle analysis and assessment approaches to their projects and providing quantitative data on the environmental impact and highlighting opportunities for improvement in this process. Lawrence has previously developed a geometallurgical model for the flotation of copper-cobalt sulfide ore from the Central African Copper Belt, and was also involved with project development for a global material solution company. So he comes with industry experience and is going to introduce us today to life cycle assessment. Lawrence, thank you very much for your time, and we look forward to it. You may proceed and tell us your story.
Okay, well, thank you very much for the kind introduction, and well, thank you everyone for tuning in this morning. So I'm going to be talking about how we could move towards a sustainable supply of metals and minerals. And sustainability has been a bit of a buzzword, I think, in the last decade. And I think that at Minviro, when using life cycle assessment, we've developed a decent approach on actually how to quantify sustainability for mining projects. Today I'll be covering the following topics. So initially I'll talk a bit more about sustainability and the awareness about the topic in the mining sector. I'll give an introduction to about life cycle assessment in the mining sector, and also talk about why it's important to not only talk about greenhouse gas emissions, and then we'll dive into two case studies. So initially we'll talk about the carbon footprint of lithium hydroxide from different natural resources. And then we'll go a bit more into the details for a rare earth element project in Malawi called Songwe Hill. And then round at least the talking session from my part off with some take-home messages. So let's start with sustainable awareness in the mining sector. And actually the timing of this webinar couldn't have been better. So last week, the London Metal Exchange announced their plan for low carbon aluminium trading. As it says in the message, it's the first time in 150 years that they're planning to actually price metal based on the carbon footprint. This isn't the first time that this has happened. So 2 years ago, back then, the world's biggest copper miner, Codelco, had the plan to sell premium copper, or at least greener copper at a premium price for customers that were interested in more sustainable practices. Unfortunately, 2 years later, that plan was ditched. If we look at sustainability, actually in the recent webinar series, it's been a topic as well. So there was one presentation mid-April that looked at carbon mitigation and carbon taxing hedging strategies, specifically for mines and minerals processing in South Africa, which I thought was really quite interesting because they also looked into actually using solar power for pyrometallurgical processes. And additionally, at the end of the month, there's 2 more webinars looking into sustainability as well. So one looking at combining exergy and metallurgical operations. And the day after, there's one that looks into the road to lower emissions. First today, I'll be talking about how we think life cycle assessment will actually add value to mining projects in development. So let's look at initially at a risk assessment done by the World Economic Forum, and let's compare the risk categories from, let's say, last decade to how it is now. So what you can see, if we look at the key at the bottom, is that 10 years ago, the majority of the risks that were identified, both in terms of impact and likelihood, were all related to either economic, technological, or geopolitical issues. And if we look at the current situation, we can actually see that the majority of the impacts, both in terms of impact and likelihood, are all climate related. So we're looking at the not responding well to climate action change, extreme weather conditions, biodiversity loss, these are all things related actually well, partially to greenhouse gas emissions. And actually, one thing that I thought was quite ironic when I looked at this picture is that pandemics were mentioned in 2007 and 2008, but I mean, it's not on the list for 2020. And well, probably a pandemic is the reason we're having the webinars right now. And the reason why this is so important for mining is because raw materials and mining are really important for the clean growth agenda. We've all heard, if you can't grow it, you have to mine it. And a low carbon future will be very mineral intensive. Clean energy technologies, they need more materials than fossil fuel based technologies. And there's also, they need materials that we actually haven't been extracting as much up to date. Additionally, we're going to need a supply of raw materials for economic development. And if we look at that, the combination of those two factors, recycling on its own is not enough to provide the resources we need. So if we look at this graph on the right, schematically, it indicates that from 2050 onwards, we can have enough material within our system to have a really high recycling rate. And we can both support both the economic development and the well, low carbon economy as we see it. And the impact of that is that demand growth for energy technology raw materials is really immense. So this is a study that was recently published by the World Bank, and it shows the incredible demand growth that we have for a range of materials, and especially for graphite, lithium, and cobalt. We're looking up to increases in demand compared to 2018 production to 500%. And that's something that hasn't been seen before in the mining sector. And one thing that's really important actually to consider from that perspective as well is that the sourcing of these materials that we want to use in the low carbon economy, they will come with direct and embodied impacts. And one thing that it's really important to consider is that these materials must not be sourced in a way that it offsets the improvement in downstream performance. As you can imagine, if we're trying to move towards an EV mobility fleet, and the materials that are actually enabling us to do that are sourced in a way that has an incredible high environmental footprint associated with it, that doesn't make any sense. So the impact of that is actually that the mining landscape is changing for the existing junior major mining companies. And what we see here in this figure on the right are the 10 major risks to mining companies as identified by Ernst & Young, which we have license to operate being one of the actually the biggest risk, and reduction of the carbon footprint is the fourth risk. And that's actually really quite interesting because in the last few years, there's been it's become more essential that for mining projects in development, understanding of their environmental risk is becoming really important for the investors, the off-takers, and the policymakers. They all want their mining companies to understand their ESG scores. And ESG stands for environmental, social, and governance. And I've highlighted the E in this case because what I've noticed in my in the last few months is that the social and governance factors are relatively well understood, but from an environmental perspective, mining companies aren't really sure how to do it. And we think that with life cycle assessment, there is a very good opportunity for mining companies to understand their environmental footprint. So let's start with the introduction to life cycle assessment in the mining industry. So how do we actually quantify environmental performance? This is where life cycle assessment comes in. And there's an official ISO definition for this. A life cycle assessment allows for a quantitative assessment of the environmental performance of a product or process over its entire life cycle. And there's been an official framework developed for this, so the life cycle assessment framework, which actually starts by setting your goal and your scope. Then you move into the inventory analysis, and then you go towards the impact assessment. And whilst you're doing these three steps, it's really important that you also continuously interpret the data that you and the methodology that you're using. And now quickly to show, for example, what it would look like in a crusher context. So in this case, we have a jaw crusher, which is powered by energy, and we have ore from the mine coming in. The outputs of the system are crushed ore and carbon dioxide. But surely, as you understand, when we move into more complex systems, this whole system, the life cycle assessment system, becomes more complex as well. And so it's always important to start with the first three things, which is define what you're measuring. In this case, we're looking at quantifying the environmental footprint for producing rare earth oxide from natural resources, from a natural resource. Then you identify your functional unit, which in this case is 1 kilogram of rare earth oxide. And then you create your system boundary, which was what we have identified here. And the system boundary is really important because it kind of sets the limit of where your life cycle assessment ends. You have the products and the raw materials coming into your system boundary. You have processes within the system. And you can, as I'm sure you can imagine, depending on how far you take it, it can get really complex. And by setting the right system boundary, you also make sure the work is manageable for yourself. So if we look at the system here, what we have within the system are the actual steps that take place on turning your natural resource into a product. So we're looking at mining, physical beneficiation, chemical treatment, separation, production, refining, and purifying until we have 1 kilogram of rare earth oxide. And associated with this, we have a number of flows coming in, which are energy, water, materials, and land. And then we have a number of flows going out as well, which is global warming potential, the use of land, the use of energy, and resource depletion. So let's move on to the inventory analysis, which is usually the most time-consuming and complex part of doing a life cycle assessment. This is the data collection phase. And all inputs and associated emissions for the system needs definition in this stage, to what extent you think it yourself is reasonable. And I'll give you an example here of the inputs and outputs associated with producing a steel slab from an electric arc furnace. And this is from a commercial software called Gabby. And you can see that it can get relatively complex quite quickly. And following and understanding the inputs and outputs and the relevant data that comes with it, it's also really important to understand the limitations of the data that you have. So within life cycle assessment, you also have this thing what we call data quality indicators. So this is what, for example, that would look like in the Gabby software. Is that what it says here? Okay, if we look at the technological time and geographical representatives, the data is very good. If we look at completeness, precision, and methodology, this is relatively good. So the overall quality of the data set is good, which is important for when you are trying to interpret the figures associated with the inputs and the outputs before you start drawing any conclusions. So if you're doing commercial life cycle assessment work, it's actually really quite important to make sure that you follow the ISO standards. There's a number of requirements and guidelines that you need to think of, and I'll outline a few here. It's important that you represent the appropriate impact categories. I've talked about carbon a lot, and carbon, of course, is the buzzword, and greenhouse gas emissions are the buzzwords of today's society. But for a life cycle assessment, it's really important that you also address other important impact categories. But I'll get back to that in a bit. If you're just using it for your internal calculations and you're not making any commercial comparisons, reviewing it internally is fine. However, if you want to actually make third-party assumptions and make claims against any data of your competitors, it's really important that you get third-party validation. And that's, in our opinion, a necessary step to avoid greenwashing. And actually yesterday, I spoke to a company that did a life cycle assessment study for their nickel sulfate, and the man that worked for the company specifically said, you must let your study do by a third party, just to avoid any, to make sure that the data is interpreted correctly, and to avoid certain relevant data not to be included. And at Minviro, we actually strongly believe in using life cycle assessment in a number, like early on in project development. So as I'm sure a lot of people who tuned in today know, usually a mining project goes from your dev study to your feasibility phases to your construction and mining and closure phases. And it's quite commonly known that the earlier you are in the process, the more possibilities you have to actually change things in your process. Because the moment you go to your construction and mining phase, the ability to influence becomes less and less and less. And we strongly believe in integrating life cycle assessments already in the field studies and pre-feasibility phases, just to make sure that you can make data-informed choices about your sustainable practices. So for this, we've developed a mining footprint calculator, which at the moment we've got one on our website, which is relatively simple and only looks at the mining phase as is. So what will be important to consider is actually the commodity that you're working on, the country that you're operating in, the grade, the amount of material that you're moving, your energy source, but of course also consumables like diesel, water, explosives, and lubricants. And with that, you can get a very quick, high-level indication of the footprint of your mining project. And we actually are currently working on a solution on developing predictive lifecycle assessment for when limited data is available. And it will go through the following workflow. A user will put in their data. The software and our methodology will indicate what data is not available at the time, which will link to an extensive database of lifecycle assessment data for existing and developing mining projects. And using machine learning and artificial neural networks, our database and will be used to extract the relevant factors for the lifecycle inventory. So in this case, we hope to automate the most time-consuming task, the lifecycle inventory, and in this way ensure that the lifecycle impact assessments, such as the greenhouse gases and water use, for example, as well, can be identified and quantified as early in the process as possible. What's also actually really important for mining projects is to make sure that the value that you're looking at is not just static, so that you say, right, my product has a carbon footprint of 8 kilograms carbon equivalent per kilogram of product. Usually for a mining project, you have different ore compositions, you have varying grades, and you have varying production schemes. And that also directly leads to a variation in life cycle, in environmental footprint over the lifetime of the project. And what we see here in the image of the right is that what the impact is of changing grade and changing unit processes on the carbon footprint of the project over the whole life of mine. And you can see that when we start in the early years mining high grades, we move towards lower grades, and we can see that the carbon footprint of the product actually increases. At the end, we see it decrease again because we stop mining and we just use the stockpiled material. But from that perspective, I think this shows really nicely why it is important to make sure that you don't just assume one static value for your mining project. Additionally, you can take this a step further, and you can actually, for each block in your resource model, you can assign an environmental footprint information. So based on physical and chemical information, such as the hardness, density, and position in the pit, you can quantify the carbon footprint or the water use per block. And in this way, take it a step further even and make sure that within your resource model, you can then put it into your in your pit optimization software and make sure that you can constrain the carbon footprint or water use of your project on an annual basis. And what we see here at the bottom are two different block models. We have one environmental block model on the left, which we can actually see that the further you move away from the initial position, the higher the carbon footprint of the blocks become. Whilst if you look at it from an economic perspective, the more traditional approach, looking at the block model, you can see that the variation isn't that big. So it's quite logical as well what you see here. I've talked a lot about the carbon footprint, but there's a lot more in life cycle assessment than just greenhouse gas emissions. Life cycle assessments allows you to quantify a range of impact categories, because like coming back to emissions, these come in different shapes and formats. For example, the carbon footprint of mining processes or electricity production, but you also need to think about particulates, for example. And there's a number of different frameworks that have been developed, which allow you to group an effect on the environment into one impact category. And what we see here on the right is what we call the recipe framework. And usually in your life cycle assessment study, you mainly focus on quantifying the impact categories. So for example, in this case, with the big star next to it, we look at global warming potential, but one that I mentioned before as well is fresh water use. And we also look at the depletion of mineral and fossil resources. And these midpoints can again be translated into the damage pathways. And in this way, you get a very good overview of what actually the impact will be of your project, not only specifically in the impact, but also onto the global society as a whole. During the life cycle impact assessment, all your different unit factors, they're converted into one unit and translated into one impact category, which is the ones that we see here on the left. So let's dive a bit deeper into water use and impact. Copper resources and mining are often linked to water-stressed regions. For example, of course, in Chile, but also in South America, this is very relevant, and in Australia, it's difficult to get the right water resources for your project. And this isn't just happening to one of mines, it's happening to all the mining companies, no matter what their scale is. And actually this morning, I was listening to a webinar from Autotech, and they mentioned that in the future, 50% of the new mines will be in water scarce areas. And what we see here on a nice image made by Stephen Northey on the right indicates the areas that are more likely to have issues with water in the future. And a number of countries that are known to be quite the powerhouses of the mining industry, such as South Africa, such as Australia, and Chile, they clearly see that these are also the countries that have a high water stress index. However, what we've noticed is that within life cycle assessment as is, the impact factors related to water are a bit difficult. They're not necessarily appropriate for what's happening within the system, and thus development of those models is actually required. And hopefully we'll be able to do that ourselves as well, but potentially also in collaboration with academia. Right, so now we've talked about sustainability in the mining sector, we've talked about life cycle assessment. Let's go into our first case study, which is about lithium hydroxide. And the reason why we're specifically focusing on lithium hydroxide is because it's a really important component of battery technology. And I mentioned previously that battery technology will be an important component of the transition to a low carbon economy. But of course, the sourcing of the materials for battery technology also comes with an environmental impact. And this is some work done from the GREET model. It actually shows, if we, for example, look at the top here, we look at the global warming potential, we can see of the battery as a whole, we can see that the cathode, the green highlighted area, almost contributes for 50% of the carbon footprint of battery technology. And the chemistry of cathodes have been a debate recently, mainly because of the cobalt content, and they're aiming to increase the amount of nickel in the cathodes. But lithium has not been a point of discussion. So that's why we decided to focus on quantifying the impact, the carbon footprint of the main different lithium sources that are available. So let's go into the life cycle assessment for different lithium natural resources. Actually, we had a webinar here about lithium a few months ago as well, which then mentioned that generally lithium comes from either brines, from the lithium triangle in South America, or from spodumene, which is mined in Australia and then converted into lithium hydroxide, usually in China, even though there are some factories to do this in Australia under construction as well. Because we were doing this as a commercial project, we also looked into the life cycle assessment of lithium produced from lithium brine, but I'll come back to that in a bit. So generally, if we look at our system boundary, what we considered is open pit mining for the spodumene processes, solar brine extraction, and solar concentration for lithium triangle processes, which then are transported to the different chemical and processing and beneficiation routes according to the company data that we had available. And then they're transported to one central location, Rotterdam, to make sure we had an equal endpoint for the transport. Materials going into the system are energy, reagents, and water. And then coming out of our system, we have emissions related due to extraction, transportation, and processing. So now let's take a look at the carbon footprint of the existing operations. And it's quite interesting because we can see that comparing the carbon footprint of Chilean brine versus Argentinian brine and Australian and Portuguese spodumene converted in China, there's a massive difference. So we can see that if we look at the carbon footprint of Chilean brine versus Australian spodumene, it's approximately 1/3 of that value, which is for a big component actually due to the fact that the energy used in China is powered by fossil fuels, but also partially because the brines in Chile use big evaporation bonds, which are solar powered, and thus don't require much actual energy being put into the system. And one of the reasons why I think this image is really important is because it shows that for a lot of companies that try to quantify the carbon footprint of their supply chain, it doesn't work to assume an average for lithium hydroxide, because depending on who you buy it from, there can be quite a large difference, up to, well, in this case, 300% difference in carbon footprint of your raw material source. Let's go back to the combination of the potential that geothermal energy and lithium have together. There's a number of projects around the world where they look at producing both lithium and geothermal power from the same source. And what we did at Minviro, we decided to compare the carbon footprint of the grid of those locations where they're considering these processes, and of the carbon footprint that would be associated with 1 kWh of energy produced from the geothermal energy. And actually, if you look at it, we can see that, for example, for Iceland, France, and Turkey, it doesn't make too much sense to extract both geothermal energy and lithium at the same time. But for California, the UK, and Germany, there's a lot of potential in both providing a critical metal and directly decarbonizing the grid. So we were asked to do some commercial work on how to quantify this for the grid in Germany and for the grid in California. And this is what it would look like. So over here on the right, we have the three existing production routes that we already discussed. And we can see that for Californian geothermal brine, the carbon footprint is approximately less than half, and this for the best current existing operational method, which is Chilean brine. And if we then go to Germany, we can actually see that because of the combination of producing energy and producing lithium at the same time from one source, we actually get a carbon negative product. So, which is caused by the way that the geothermal energy offsets the current carbon intensity of the grid. And this is really interesting because, yes, in this case, it only applies to lithium and to lithium from geothermal deposits, but it can also be applied to similar projects that have a unique feature like tailings that sequester carbon, or a process in their flow sheet that captures carbon. And that way you can offset the eventual footprint of your product, which is really beneficial from in case you speak to your off-takers. Okay, so now let's move to our second case study, which is a non-operational pre-feasibility project in Malawi, looking into the production of a rare earth oxide called Songwe Hill. And what we did in this case, we decided to link process simulation with life cycle assessment to assess the difference in carbon footprint for a number of different technical solutions. So normally in your pre-feasibility stage, you have a flow sheet that's based on data from either literature or from your engineering studies. And you can combine this with well, process simulation software to obtain a closed mass balance, which will give you the masses moving around into your system, the water and energy inputs. And then you can very easily export this data and in this way obtain your life cycle inventory. So we did that using a software called HSC Chemistry from Autotech, and that allows for direct exportation of the mass balance results, which you then can combine with life cycle assessment software Gabi. And this way you can get actually quite a good quantitative oversight of what the carbon footprint will be of your different solutions. And we decided not to focus too much on actually, we know this, we knew from the engineering study that this, that the mining and beneficiation process was relatively well defined. So we decided not to focus too much on that. We said that was standard. So that's what we have here, the system boundary. So what we have within the system from a project perspective, we're looking at the mining, the crushing and milling, flotation, then we go into our leaching and dissolution, then we go into the precipitation phase, and additionally we've also looked into the on-site waste management and to what extent asset regeneration and generation on-site would actually add value from an environmental impact perspective. And using the Gabi software, we had the possibility to look at what the impact is of process materials, ancillary materials, and what the production and distribution of energy would be for the project. And one question that we actually really wanted to answer is, to what extent can we obtain our kilogram of rare earth oxide with either a high or a low carbon footprint? So we decided to leave the flow sheet actually out of the equation in this case, at least the technical solution to produce the material. But we decided to look at more technical viable solutions that we could change within the infrastructure without influencing the rare earth oxides production flow sheet. So what we did, we looked at what the difference would be in producing acid on site or importing fresh acid, because burning sulfur has a exothermal reaction, so you also have the possibility to generate energy. And we looked at different energy solutions. So do we want to produce energy on site? Do we want to connect to the grid? Well, in Malawi, the grid's a bit unstable, so you would need to have some support energy anyway. And to what extent, what would the impact be of placing renewable energy combined with battery storage on site? And it was really quite interesting, because in the best case scenario, we're looking at a result of 17 kilograms of carbon dioxide equivalent per kilogram of rare earth oxide. And in the worst case scenario, we're looking at 87 kilograms of carbon dioxide equivalent per kilogram of rare earth oxide. So it's nearly 400% difference in greenhouse gas emissions. And this is even without considering the reagents that come into play. This is just by ensuring you set up the infrastructure in such a way that you're being as sustainable as possible. So what we also did, we decided to look into the unit processes that contribute to climate change. And this was also really interesting, because what you can see is that for the best case scenario, so for the 17 kilogram carbon dioxide per kilogram of rare earth oxide, approximately 10 kilograms of carbon dioxide comes from the precipitation phase. So what you see here, it's more than all the other factors combined. And if we then follow like the key at the bottom of the image, we can see that approximately 80% of the carbon footprint of the precipitation phase is due to the use of sodium hydroxide. And then if we now think back to earlier when we discussed how we at Enviro see value in using life cycle assessment early on in the project phase, this exactly highlights why it's important. Because if there would have been possibilities to reduce the use of sodium hydroxide, maybe find an alternative, it would have highlighted areas that the engineering firm would have needed to focus on to reduce the carbon footprint. And actually, our initiative was received recognition from the European Commission, who said that integration of life cycle assessment in the mining project design stages can be really valuable for the policymakers of making sure this becomes part of the routine processes where projects and engineering firms, project teams and engineering firms actually think about the life cycle impacts throughout the project development phase. So let's conclude with some take-home messages. So I think what's quite important, sustainable awareness in the mining sector is growing, driven by society, investors, off-takers, and policymakers. We all know that metals are key to global decarbonization, but it is really important that the materials are sourced in such a way that it does not offset the downstream performance. We've also seen that the same product from different natural resources is likely to have a different environmental footprint. And hopefully I've also shown to everyone on the webinar today that the life cycle assessment can be used to assess the environmental footprint of a mining project and highlight areas of focus and provide opportunities to reduce that environmental footprint. Thank you for your attention.
Thank you. That was very interesting, and we really appreciate your time to put this together for us. It's always nice when somebody is familiar with something so complex that can explain it in quite very understandable language to the rest of us. So from my perspective, listening to today's discussion, it just reminded me that the power of this tool could be quite useful in early stages of mining projects, rather than just looking at something that's already operating, which you don't often think about. You think about life cycle assessments for existing operations, to see how can we reduce it. So I think there is quite a big value for us.
Good. Oh, I'm glad that message came across.
Yes, I definitely, it made me really think. We often, we do our feasibility study as engineers, and you say what's the best for the process, and you try and minimize your footprint, but there's definitely room for adding a life cycle assessment to the toolbox.
Okay, I'm very glad to hear that.
So I think you did a really good job. I don't know if there's any questions from the panels or from the attendees. Is there anybody who would like to ask a question? Please feel free to either put it on the Q&A or the chat, but I don't know if you have some closing thoughts for us.
Not at the moment. Well, there's no questions. I think, well, I'm really happy that it came across that what the impact, the quite literal impact of life cycle assessment can be in project development. And yeah, if anyone wants to get in touch and discuss with us what the value of that could be, well, you can reach me on the email address here or connect with us on LinkedIn or anything along those lines.
Yeah, so I mean, it was very interesting because we also recently had a presentation on a lithium project and how it works, the whole solar process. So it was quite interesting to see it. There's some questions popping up now. Do you have some figures, idea of the figures of the downstream CO2 credits with the use of lithium? So I think if you're using lithium in your manufacturing or processes, does it have an impact?
Sorry, could you repeat that, please?
So the question is, I'm going to read it word
Yep.
for word. Do you have some figures for the downstream CO2 credit with the use of lithium?
Okay. I do have those figures, not in this presentation, so we have them available ourselves. So that refers to the use of lithium, I think, in the battery technology that I showed in the slide. So yeah, we do have those figures, and we didn't quantify them here, but yeah, if you get in touch, I'll be happy to share them.
Okay. So so there's a question on the chat that how much value is put on being green by investors? I mean, if you choose between two options with the difference in NPV, how much does being green compensate for the difference? So, I mean, obviously it's sometimes more expensive to build a greener plant.
Well, that really depends. So renewable energy is becoming much cheaper as it is now. And so from that perspective, and also when we start moving on, like if we move towards the reduction of diesel use in mining fleets and making those electrical powered, you can actually get, I think, relatively cheap power for your mining process. And from that perspective, the NPV wouldn't necessarily have to be negatively influenced.
Yeah.
I do know what I've heard in conversations is that depending, of course, you have different types of investors. you have specific green bonds as well. So if you can show that you actually have a much greener process and maybe a lower MPV for them, it will matter. For your traditional investor, what we've noticed is that they of course care about the MPV, but as long as you can provide them a good estimate of the impact of your project, they'll be happy as well. And that's already really rarely happening. So that's also where the life cycle assessment approach adds value, because you provide the investor the information it needs.
Yeah, I think that's very true. I've seen some interesting questions from investors, even, like people who produce large volumes of technology products like phones are starting to look at the clean metal production value chain all the way back down to even the ore. So you could be making an iPhone, but they want you to use cleaner metals to build it. So I think that investment appetite will definitely grow as we go forward.
Yeah, absolutely.
This is a very nice question. What are some of the questions one should ask when establishing the system boundary?
So it's really important for yourself that you understand what you want to study and what you want to quantify. So that just by setting the goal, you can quite clearly define what the system boundary is going to be. So for generally, if you say for yourself, okay, we're assuming a regional value for the inputs going into the system that we know are not related to the project ourselves and to the flow sheets and to the mining process. From that perspective, you can quite easily exclude that part from your system. So usually we do it for mining projects, and then what we tend to ask ourselves is what components are directly influencing the carbon footprint or the environmental footprint of the product. And to what extent can we influence one of those factors? And if we can still influence it, we tend to be able to include it in the system boundary.
Yeah, that's very, very well answered. Thank you. So here's a question about the anonymous attendee is asking, I recently came across an SLCA. Was just wondering what Lawrence think about this.
What type of LCA, sorry?
SLCA.
Oh, I wouldn't know what it is. That's embarrassing.
Well, sorry, I don't know either. So we'll some homework for you.
Yeah, and well, if the question asker wants to get in touch, I'll happily discuss it as well.
I apologize, I'm going to have some background noise. So perhaps we will have to wrap this up. There's power failure in our area.
Okay.
Question that's very interesting. How would you consider labor as an input? For instance, more labor might be more impactful, yet also help socially.
Sorry, can you ask the question again?
How would you consider labor as input? For instance, more labor might be more impactful, yet also help socially.
Right. Okay. Yeah. Social factors are always a bit more difficult to quantify. So we always tend to focus mainly on actually the environmental side of things. In the end, I think you, as a mining company, you always will have. You need to make sure you positively influence the social side of where you're operating at that point. So you must make sure that you create jobs. And I think commonly, if you look at a mining project, you're always looking at making sure that your trade-off between labor and costs, and then hopefully in the future also environmental footprint, is optimized. So I think usually I wouldn't say it's a difficult, it's a point of question, because you always need labor, and you always need technology, and you always have an environmental footprint.
We had some clarification on the SLCA is actually for social, so
okay.
that might help.
Well, my answer remains the same. I'll need to have to look into that and see what it exactly means. We do at Minviro tend to make sure we don't focus too much on the social side of the mining projects. Reason for that being is that we think it's really quite difficult to compare environmental impact data with social impact data. I'm sure that the social life cycle assessment will have a lot of value, but it may not allow for a direct comparison with environmental impact data, and that is our specialty.
In your experience, how secretive are companies about their information? Because that, you know, there's a lot of information that would be quite helpful for an LCA study. So one of the attendees is asking, what is your experience about openness?
Well, generally, mining companies indeed really are not open about their environmental footprints of their projects. So from that perspective, you would need to team up either with the company or with an engineering expert that can tell you a bit more about what is more likely to be, what is the process to be used, what is the water use, what's the amount of material they put into it, and what's the energy they put into it. It's definitely possible to nowadays, using the sustainability reports, to make some decent assumptions about it. It's not easy, but it is possible.
Okay, so I think one of the last good questions for, so as a conclusion perhaps, is in terms of how do you see the future of this process, as life cycle analysis, going forward for the global mining projects that we are going to can see in the future?
It's a really good question. It will really depend on the policymakers. Life cycle assessment, of course, is a really useful tool to quantify, but you will also need an LCA expert in your team to quantify it for you, and that makes it quite tricky. Hopefully, by ensuring that the knowledge within the in the mining sector, within the normal, like let's say your normal mining employee, that he or she gains some information about how it works, and by providing the right tools and with the right pressure from the policymakers, we personally hope it's going to be a standard part for companies and for governments to understand what actually the impact of mining is.
Yeah, I think your comments are very wise. It's one of the things that makes life cycle analysis so challenging is that it is a complex system that you're working with.
Absolutely.
So you can't just dabble. You can't just dabble in LCAs. You have to actually have a team's expert involved. Otherwise, you could draw very bad conclusions from the work.
Yeah,
so,
that's why often from a third-party perspective, it's really useful to get their insights and not do it too much internally without people having the knowledge. Otherwise, things are forgotten or neglected intentionally. It's possible as well, of course.
Yeah. Well, I mean, it's a very, very interesting conversation, and I hope that we can host you again in the near future, talking about more, maybe more details. I think there's a lot of these, honestly, SAIMM is going to host a lot of online schools and events, so we'd love to have you join us for one of those as well. So from my side, thank you very much for a very, very interesting presentation and for your time, spending it with us today.
Okay, well, thank you as well for having me today, and well, have a good day, everyone, and thank you all for tuning in today.
Yes, and attendees also thank you as well. Thank you. Have a good day.
Bye-bye.